Hello, and welcome to Module 8.7, Exponential Equations. Our objective for today is that I can solve exponential equations. Our vocabulary: what is an exponential equation? It's an equation where the independent variable is an exponent. So the variable that you are in control of is the exponent. Now, we've got the power property of equality. For any real number b greater than 0 and b not equal to 1, b to the x is equal to b to the y only if x equals y. Well, okay, what does that mean? So if we had, for example, 4 to the x is equal to 4 to the fifth power, then we know x must equal the fifth, x must equal 5, because then it would be 4 to the fifth equals 4 to the fifth. If n is 2/5, 5 to the n power equals 5 to the 2/5 power. If x were 1/2 and we had 3 to the 1/2, then x must equal 3. We need to have the same base and the same exponent for these two things to be equal. So solve a one-step exponential equation. All right, so we've got 5 to the x, and that's equal to 625. So what we need to try to think about is we have 5 to the x, and if we write it in our the way we had our property of equality up there, so we have 5 to the x is equal to 5 to the something. 5 to the something power is going to give me 625. Well, I know 5 squared is 25. 5 cubed is 125. 5 to the fourth is 625. So I write it as 5 to the x equals 5 to the fourth. So now what does x have to equal? X must equal 4, right? So what we're doing is we're creating this power that is going to be able to set us equal on both sides of the equation. We're trying to figure out what power 625 is of 5. All right, letter B. We have 2 to the x power equals 512. All right, so we rewrite it as 2 to the x is equal to 2 to the something. Okay, what is that something? Well, we start with 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. Okay, we still haven't gotten there yet. Times 2 again is 128. Times 2 again is 256. Still haven't gotten there. Times 2 again is our magic number of 512. That was, if you were counting at home, 9 times that we multiplied by 2. So that means our x must equal 9. All right, letter C. We've got 3 to the x is equal to 243. So we have 3 to the x is equal to our common base, 3. Well, what are our factors? 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 243. So that was a total of 5 3's that we multiplied by. So now we know that our x value must be 5 in order to make that equation true. All right, you're going to try letters D, E, and F on your own, and then check your work against mine. So letter D, we've got 3 to the x power is equal to 3 to the something power. Now, we just went through all of our multiples of 3, and we found that 3 to the fourth was equal to 81. So that means x is equal to 4. Letter E, we've got 4 to the x power, and we want to know what power of 4 gives us 64. Well, 4 times 4 is 16, times 4 is 64, so that's 4 to the third power, so x must equal 3. And lastly, letter F, we have 6 to the x power is equal to 216. So we have 6 to the x power is equal to 6 to the what? Well, 6 times 6 is 36, times 6 is 216. So that's 6 to the third power. So this is another one where x is equal to 3. All right, now example 2, we need to solve a multi-step equation, and these get a little bit weird. So we have on the left 27 to the x minus 1 power, and that's equal to 3. Okay, that's weird. So let's think of it as this is equal to 3 to the first power. Still kind of weird. But do I know something? Do I know a relationship between 3 and 27? I do. I know that 27 is 3 to the third power. So what I'm going to do is I'm going to rewrite 27 as 3 to the third power in parentheses. So all I've done is I've taken 27 and now I've represented it a little bit differently. I've represented it as 3 to the third power, and it's in parentheses. So it's telling me that has to be done first. 3 times 3 is 9, times 3 is 27. And now I have the x minus 1 in the numerator, and that's going to be equal to 3 to the first power. Now you might see where we're going with this. We're going to multiply our exponents up on top here, the x minus 1, we need to multiply that by 3. So when I go ahead and do that, I get 3 to the 3x minus 3 power is equal to 3 to the first power. Okay, now what do we do? Well, before I was able to just say x is equal to something. Well, in this case, my exponent, 3x minus 3, is equal to 1. Okay, 3x minus 3 equals 1. And now, guess what? We are all the way back into module 2, and we are solving a two-step equation. We add 3 to both sides. 3x equals 4. Divide by 3. And x is equal to 4/3. So if you really wanted to go back and type in 27 to the 4/3 minus 1, so essentially 27 to the 1/3, you would get 3. Hey, guess what? 27 to the 1/3, that's a cube root of 27, and that gets you 3. There we go. Our work checks out. That's the beauty of some of these. We're back into the world where you can check your work and verify that your answer is correct before you move on to the next one. All right. Letter B, we've got 3 to the x minus 3 power is equal to 243. Okay, well, we've got our base is as small as it can go. We really can't break that into any factors. We have x minus 3 up there. But this 243, I can write that as a factor of 3, right? So let's think back to the ones that we did a little bit earlier. We saw 243 in letter C in example 1 to know that that is x or 3 to the 5th power. And now we just rewrite our exponents as x minus 3 equals 5, right? Our exponents must be equal to each other. And all we have to do, one-step problem, add 3 to both sides, x is equal to 8. And we double check. 3 to the 8 minus 3. 8 minus 3 is 5. 3 to the 5th power, 243. All right, letter C, we have 2 to the 5x is equal to 8 to the 2x minus 4. Well, nothing to do on the left side here. So we have 2 to the 5x. 8, I can write 8 as a factor of 2, right, as a power of 2, and that's 2 to the 3rd power to the 2x minus 4. And so now we multiply the 3 by the 2x minus 4, and we get 2 to the 5x is equal to 2 to the 6x minus 12. Now, can I go back and I can do 5x equals 6x minus 12. So I subtract 6x from both sides. I get negative x equals negative 12, and I divide by negative 1. X is equal to 12. And if you go back and you do the work, 5 times 12, raise 2 to that power, you can do that. 8 to the 2 times 12 minus 4, so 2 times 12 is 24, minus 4 is 20, 8 to the 20th power, and 2 to the 60th power, and you will get the same values. All right, let's flip to the next page, and you're going to do the 3 U-try problems at the top. Go ahead and go, and then check your work against mine. All right, so now we're going to go ahead and get started with letter D. We have 4 to the 2x minus, or 2x plus 1, and we have 1024. All right, well, let's see. We have 4 to the 2x plus 1 is equal to, okay, I know this has to be a multiple of 4. It's not something we've seen before, but we know 4 times 4 is 16, times 4 is 64, times 4 is 256. We've already been to there. Times 4 again gets us to 1024. So if you were checking, that is 5 4s. So now we have 2x plus 1 equals 5. Subtract 1 from both sides. 2x equals 4. Divide by 2. X equals 2. Letter E. 2 to the 4x plus 3 equals 128. So we have 2 to the 4x plus 3 equals 128. That is going to be 2 to the 7th power. So now 4x plus 3 equals 7. Subtract 3 from both sides. 4x equals 4. Divide by 4. And we get x is equal to 1. All right, now letter F. We've got 2 to the 4x power. We've got 32. Well, 32, that's 2 to the 5th power. So we have 2 to the 5th and times x plus 1. So we have to multiply. So we have 2 to the 4x is equal to 2 to the 5x plus 5. And now we have 4x equals 5x plus 5. Subtract 5x from both sides. We get negative x equals 5. Divide by negative 1. And we get x equals negative 5. Okay. Any questions there? All right. Now, example 3 is solving a real-world exponential equation. In the 1950s, scientists proposed a space station that could house a crew of approximately 80 people. The station could produce artificial gravity by rotating at a speed of w equals the square root of gr, where g is 32 feet per second squared, and r is the radius of the station. If the station's design required a rotating speed of approximately 64 feet per second to simulate gravity on Earth, what would the radius need to be? Okay, well, let's substitute in what we know. So far, I know that g is going to be 32 feet per second squared. I know that my speed, rotating speed of approximately 64 feet per second. Okay, so that would be our w. So we know w, we know g, we're trying to find r. So let's write our equation. So w, our speed, is 64, is equal to the square root of g, gravity, 32. That's the gravitational constant for Earth at sea level. That is your gravitational constant in feet per second. It's not what we use in science usually. Usually we'll be using metric, and that'll be 9.81 meters per second squared. Anyways, I digress. So we have a 32 times r. So we need to isolate, or we need to get our variable out of inside the radical. So what do we need to do that? Well, undoing a radical would be squaring both sides. 64 squared is going to give me 4096 is equal to 32r, right? Because when you square a square root, they cancel out. And then we just divide by 32. 4096 divided by 32 is 128 feet is equal to r. So the space station would need to have a radius of 128 feet in order for it to have that amount of gravity at that rotational speed. So that's a pretty large space station. All right, letter B. The degree to which sunscreen protects your skin is measured by its sun protection factor, or SPF. For a sunscreen with an SPF of F, the percentage of UVB rays absorbed, P, is P equals 50R to the 1/5. What SPF absorbs 100% of UV rays? All right, important information. So I want to know, let's see, SPF is F, right? So that is what SPF. We're trying to find F. We know that we've got 100% of UVB rays. So UVB rays absorbed is P. So we're going to substitute in 100 for P. So we're going to have 100. We want to know, what is it when it's 100% effective? And that's going to be equal to 50 times R, yeah, sure. R is going to be our unknown, and then it's 1 to the 1/5 power. Now, the first thing we should do to solve this, we're going to divide both sides by 50. Okay, so we're going to divide by 50, and that should be F, not R. So F to the 1/5. So we divide both sides by 50, and when we do that, we get 2 is equal to R to the 1/5. Now, how do we get rid of the 5th root? We raise it to the 5th power. And when we do so, 2 to the 5th power is 32 is equal to our F, and that is our 32 is our SPF. So if you have a 32 SPF, it is going to absorb 100% of the UVB rays, assuming that you apply it properly. And by the directions that are on it, so it means you reapply it every so often, pay attention to water usage, all of that kind of stuff. So that gives you an understanding of what the SPF factor and how that all actually works. All right, so this is another kind of interesting one. It gives us a little bit of a tour around the world. So on the Indonesian island of Bali, there are numerous villages that surround the Undla River. And there are several weirs which measure and control water flow. You see a weir in the picture on the right there. It's basically like a long rectangular dam that the water flows over the top of. If you drive by the Fox River in Geneva and St. Charles, you can see some examples of these weirs there as well. So they prevent flooding and protect the villages. To calculate the flow of water in cubic meters per cubic feet per second for a rectangular weir, you can use the formula Q equals 1.6 LH to the 3 halves, where L is the weir length in feet and H is the height of the water in feet. So we have some information now. So all of that was just set up for our problem. L is the weir length in feet. Well, we know we're being told our weir is 2 feet long. So that's our L. All right, our flow rate we're being given. Our flow rate is 86.4 cubic feet per second. Our flow rate is Q. And H is what we want to find. What is the height of the water? H. So let's substitute in the values that we know. We know that Q is going to be 86.4 feet per second. That is going to be equal to 1.6 times the length. The length is 2 feet. And this is times the height to the 3/2 power. So first step that we would have to do here, obviously, is we're going to multiply 1.6 times 2. So we get 86.4 equals 1.6 times 2 is 3.2 h to the 3/2. All right, now the next thing we do is divide by 3.2 to get our variable by itself. Okay, and when we do that, we are going to get, let's see, 27 is equal to h to the 3/2 power. Our final step is going to be raise everything to the 2/3 power. So we're raising it to the 2/3 power. And when we do that, you're going to go ahead and just use your calculator on that. We get 9 feet is equal to our h. So our height of this weir in the Undla River in Bali, Indonesia, is going to be 9 feet tall and 2 feet long. All right, so not very wide, but it is somewhat substantially tall. All right, that's the end of our notes for this module. If you have any questions, please bring them to class tomorrow. Otherwise, I hope you have a great day.